Okay, so I'm going to be talking about asynchronous programming and what that means in the R world and how we can use it in Shiny applications. My name's Russ Hyde. I'm a data scientist at Jumping Rivers, primarily working in Shiny development, but also a little bit of more kind of typical data management and data science type work. As a firm, we specialize in data science training, and things like the kind of infrastructure that makes data science possible. So we have a lot of experience um, supporting the kind of professional POSIT services and deploying them for clients as well. We have um, a conference that's coming up in October called Shiny in Production. This is a way to highlight some of the aspects of Shiny development that may not go that may go unspoken in some ways. How do you deploy things effectively? How do you make your applications tolerant to hundreds of users and things like that. The not just the building of applications, making them so that they're professional grade things that people can readily use. That's at the start of next month in Newcastle upon Tyne in the UK. There is a QR code on the left hand side here. I'll show it again at the end of the talk. And there is a discount code to get 30% off the tickets there. We also specialize in training for data science. So the typical languages that you might use as a data scientist, Python and R, and for interacting with databases, SQL, and also project management type things as well. If you're interested in that, we have a discount code for training material as well, and that's shown on the screen. And again, I'll show it at the end. But today we are talking about Shiny, um, and how asynchronous programming can make applications that you've written um, a more pleasurable experience for the user. So why have I got a title page up here that indicates that Ala's going to become a chef? Well, a lot of the things that you need to think about with regards to asynchronous programming translate quite nicely to a professional kitchen. Um, Typically, with a Shiny application, you have a single R session running on a server somewhere, and you might have multiple users concurrently accessing that thing, that R session. So R might be supporting processing required by user one, user two, user three at any point during those user sessions. But there's a single R session involved in the whole of that. Um, so the more effectively we can make use of the time that R session is up and running, the better. Now think about this. If you're developing Shiny applications, you have probably got to there by doing typical scripting type R development. Um, so you might have written code in a .r file or in a R Markdown file or something like that. And what happens when you run an R script is typically that they're processed line by line. The first line will run until it completes, and then the second line will run until it completes, and so on, until you get to the end of the script. With Shiny, it's a little bit more complicated because users will interact with an application and cause different parts of your source code to run at different times. But if you think about this little process, we're making a dish, a chili and some rice and maybe a side dish. The different processes there take different amounts of time. It might take 20 minutes to cook some rice. It might take an hour or so to cook some chili, and a few minutes to make a side dish. The different amounts of work involved uh, in your kitchen uh, uh, are quite important as well. So to make rice, it's quite a hands-off process. You can put some rice in a pan and leave it to boil for a while. With chili, you might need to prepare some vegetables and whatnot, and so there might be some preparation, there might be some cooking. It's not all hands-on work. A lot of the processes that we use um, in application development and stuff, some of them are very hands-on. They require a lot of processing by your infrastructure. And some of them are quite hands-off. They might be a call to a database somewhere distant. They might be a call to an API that you don't own. And those are the kinds of things that you can wait for, but your R session doesn't really have to do anything while they're running. This little recipe here could reasonably be done in 70 minutes rather than the sum of those things, rather than 95 minutes. Because there are processes that can go on at the same time as each other. In this little webinar, we're going to talk about asynchronous programming. We're going to talk about the basics of what that are, the tools that are available in R. We're I'm going to mention futures. I'm not going to talk about promises much. We're going to only talk about it in passing, and we're going to briefly touch on parallelism. Um, and but the main thing is what the problem is that asynchronous programming solves for Shiny, and that's something called blocking. And there's a tool called Extended Task available now in Shiny that is the go-to tool for solving this blocking problem. Um, I have a application that kind of illustrates the problem that might arise. So here we have um, basically the same um, thing as I've just presented as an R script. If I wanted to order, say, let's say 10 portions of a dish from a restaurant, they would need to cook the various components of that. And cooking those different components will take different amounts of time. This app works in a sequential way. So it will, when I order some chili here, it will cook one of the things, and then it will cook the other, and then it will cook the other sequentially. Okay, so if I run that, I get some little messages up saying it's now cooking some chili. That will take a few seconds. When that's complete, it will start cooking the rice and then the side dish and things like that, each one in turn. While that sort of stuff's going ahead, I can't actually do anything else in this application. If I clicked on show the menu here, that doesn't do anything. The the process that's kind of computing, well, it's computing, but for our sake, it's cooking some dish components. Clicking on this other button does nothing in the Shiny application until this ordering process is complete. And actually, if we had two users using the same app at the same time, and one of them ordered something from the restaurant, and the other attempted to order something from the restaurant at the same time, it would only be once all of the processes for user one had completed that any processing started for user two. So user one's computation is blocking user two from doing any useful work. we'll come back to that later. Okay. Um, Asynchronous parallel programming. Importantly, we're talking about asynchronous programming, but in R, the way that we can access those kinds of techniques is through parallel programming, through using um, uh, the independent processors that are available within your computer, within your server. So again, to come back to our scripts, this is a typical script, and the way that the R interpreter would work through it is from top to bottom. This line here, where dataset 1 is obtained, that will run to completion before we obtain dataset 2. Okay, that runs to completion, then the next line runs to completion, and so on and so forth. With parallel computing, the members of the audience may have some experience of this, and a typical task that you might use parallel computing for in R is to say if you had a list of data, multiple chunks of data in a big list in R, and you want to process each component of that list using the same function. Sequentially, you could process the first element and then the second element and the third element, and it will take as long as it would to process a single element multiplied by the length of the list, basically. But my computer, I could reasonably spread work over 16 different processors. So that list I could split in half and do half of the processing on one core and half on another core. And that would potentially double the speed of the calculation. And we can combine, and once all those calculations are performed, be they over potentially multiple cores, we pull the results back into the original R session where the computation was started from. So that's parallel computing. There's nothing asynchronous about what I've just described. You're just spreading workload across the available processors on your computer. Sequentially processing a list or any other kind of collection, you could use the map functions from the per package. So here we're using map to iterate over the numbers 1, 2, 3, and 4. And each time we're going to apply a function square to the numbers. Any experienced R programmers would know that you can compute the square of a vector of numbers without having to map over it. But this is just a kind of illustration. At the end of running this, we'd end up with a list with the square of 1 and the square of 2 in the corresponding positions in that list. We can readily parallelize the same code and take advantage of multiple processors by using the fur package. Fur provides functions that are very similar to those in per, named similarly. So here we've got something called future map, which corresponds to the map function in per. In order to use fur, we need to tell our R session how many additional workers, how many additional processors we can take advantage of while doing the kind of parallelized processing. So we have to set up some tooling in order to split our work across multiple R sessions. right? So that's parallelized code. This actually uses, under the hood, it uses asynchronous programming, but it isn't visible to the user. Now, if we wanted to, we could time how long a script takes to run. And for a sequentially processing script, it takes as long as each task within that script takes to run, summed together. So in order to time the script that I presented earlier on, it would take however long it takes to obtain the first data set, plus however long it takes to obtain the second data set, and then all the subsequent times as well. These two steps could readily be parallelized. You could pull the data set one in through one R session, pull data set two in a different R session, and then pull those results into the main R session or something like that. And asynchronous programming allows that kind of thing. Timing the a parallelized version of that original script could, if we parallelized just the obtaining the two data sets, that could take whatever the maximum of the time it takes to do these two processes, plus the time that it takes to do all these um, subsequent processes. Um, and that, depending on the data set, that might really speed up the script. But there we're parallelizing the different function calls rather than the same function call across a collection on of a list or something. So how do we actually do that in R? Um, so the conceptually, what we do is the following: we hire a bunch of chefs, and we get our first chef to do one aspect of the dish. We get our second chef to do another aspect of the dish, and so on. And we wait until they complete, and then we can build all those dishes together. That's conceptually it. The chefs here are the processors on our computers. The future package is how asynchronous programming is done in R, and and the example I show later related to Shiny will make use of future. So you saw this code earlier. We define a plan, which is how you specify in R how many additional processors are available to us that can do work. In order to send work to those processors, we use a function called future. And the beauty of this future function is that it doesn't block any subsequent lines in a script. So if this is a script, R would interpret from top to bottom still. When it gets to this point here, where you've defined a future that will cook that chili for you, it doesn't have to wait until it's finished. It can go on to the next line and start another process, maybe to cook some rice or something. I've put in a little line at the bottom here that blocks the the script until all of the futures are complete. Now the thing about a future is it defines some code to run and starts that code running, but it doesn't wait until that code has finished. If you need to make sure that your code has finished running, you have to put in some checks. Shiny will handle that for you, and I'll show you how that works later. But this future call will immediately return to you, and the script can continue without waiting. Now, I can show you an example of this, of how that can speed up some code. if I go into parallelizing R, a sequential recipe, right. So I've got three different functions here. They pause the R session for 2 seconds, 7 seconds, and a half a second. If I run this piece of code, this script, the code will evaluate sequentially. The first thing for making rice will run to completion, and then the next line will run to completion. I'm using a package called TikTok to time how long that takes. So if I run all of that code, you can see it takes a few seconds for chili to run, to be created. Then it takes, and in total, it takes 9.5 seconds, which is the sum of all these different pause steps that I put in. So that's sequentially running a script. You'll have done that before. Um, to use asynchronous programming, as I just showed in the slides, we're using the same function definitions, the same pauses, and things like that. And I'm using TikTok again to time the uh, the processing. So I'm going to run this whole thing. When we get here, you should see that the rice, chili, and side dish futures, they return immediately. There's no blocking, and we go straight down to this line here. So if I run that, all three of them returned immediately. Now we're waiting here, this future value thing. Now I wouldn't normally use that in production code, but it's quite helpful. It allows us to block and wait for those three futures to finish before continuing. The whole thing took 7 and a bit seconds, so faster than the 9.5 seconds that the sequential version took. And the reason it took 7 and a bit seconds was because, the longest process in there must take 7 seconds. Um, the three different function calls overall take a little bit longer than 7 seconds. But they're evaluated independently. The rice is made on one processor, the chili is made on a different processor. Okay, right. I've labored that point enough, I think. Let's go into Shiny. Now, when a script is evaluated, and we're using parallel synchronous code like lapply or future map or something like that, what happens is we get to the point where the code is parallelized, and then we have additional R processes doing work. Those things start working, and when they've all completed, only at that point can the main R session carry on with its work. Only once everything's complete can the R session, the initial R session complete its work. So that's parallel synchronous code. These are processes, additional processes running some R code. When they complete, they return to the main R processor. And we're interested in asynchronous code. What happens in a similar situation is we might define a bunch of futures that, again, run on parallel processors. But rather than blocking at the point where the futures are defined, the R session could continue working. There may be, and that's how we managed to run the chili future and then the rice future and then the side dish future one after the other without any pause in that last example. So with asynchronous code, we can return back to the R session. It can take control and continue working. And that's really useful in Shiny. Because with Shiny, like I was saying earlier on, you have a single R session that potentially supporting 10, 50, 100 users. concurrently. Um, and the work that one user asks that R session to do can prevent um, a second user from asking the R session to do any work. To visualize that, what might happen is um, request from user one's browser gets sent to the R session. Hey, Shiny, can you do this? And Shiny says, no problem, but it's going to take some time. And it's either doing a big calculation or it's calling an API that might take a long time to return. During that time, it's quite feasible that user 2 might be asking Shiny to do something else. And if the R session is busy, it can't respond to requests from other users. It'll any additional requests that come in, it'll wait until it's finished its current computation to respond to them. So that's between session blocking, one user preventing another user from doing anything with an app. Within session blocking, I illustrated in the app at the start of this session. So here we are telling the Shiny session to do something. It might be a long computation or something. And it can do that. But if you ask the app to do something else, like it did when I asked it to print out the menu for the restaurant while it was cooking what I'd already asked it for, it couldn't do that because it had no way to respond to additional requests because it was busy processing stuff. And that's solely risen because the back-end logic of a Shiny app typically runs sequentially in a single process. But we have access to lots of processes. So it's quite feasible that user 1, 2, and 3 could make requests of a Shiny app, and those requests be handled by parallel processors rather than by the main Shiny session. And that's what we use asynchronous programming for in Shiny. Okay, so we've got the possibility of user 1 making a call to the Shiny app. Anything that user 1 needs computing could be done in a parallel asynchronous task. And when it's complete, the Shiny app get updated for user 1. But during that time, user 2 could still talk to the main R session. And the tooling underpinning that is called extended task. Extended task was introduced to Shiny at the spring of 2024. And it prevents both of the types of blocking that I illustrated in the previous section, between session and within session blocking. Importantly, once extended task, it's an object that you can use to run some code, and it will run it in a kind of parallel processor in a way that won't block the main R session. It uses futures underneath it and actually uses something called promises. And conceptually, what a promise is it's a way in the main R session of handling a result that's been computed in a parallel asynchronous way. Okay, so we don't really need to know much about promises to understand the code that will follow. It's got quite a clean syntax. There's an older way of handling between session blocking that extended task has kind of eliminated the need for, but you might find in older Shiny code. Let's have a look at how it works, though. A Shiny app, conceptually, is a bunch of variables hooked together with dependencies between them. And when you get a change in the value of one of those variables, it bubbles through anything that depends upon it. So here, if the user enters a value for input $X, that value affects the value of A. A will get updated in response to input $X's value. And then when A changes its value, B will have to change its value. There's a dependency between all the variables. There are also blocks called observe blocks and event reactive blocks and things. And what these do are they respond to changes in a variable, and they run. You can run arbitrary code in those blocks, and that might mean that you update a reactive value or have some other side effect within the app. Extended task sits outside of this reactive graph. So it's an object that you define, but you'd define it within your server session, but it is something that sits outside the reactive graph. And the way that you use it is, rather than say updating the variable C directly from in an observe block, you would invoke an extended task that tells the extended task that you want to run a piece of code that it itself has defined. And you can make a variable C, a downstream variable, depend upon the result of that in the same way that B depends upon A and A depends on input $X. I can show you a concrete example of that in the next slide. So the syntax looks like this. You define a new extended task, and that takes as its main argument a single function. That function has to be an asynchronous thing. It has to be something that we can evaluate asynchronously in a separate R process. Here, in response to clicking some button, we're going to start that inner function in the extended task from running. Okay, so on clicking a button, this might start this function running in a separate R session. When the result from running that function is ready, we can get it back into our Shiny session. Okay, so you've separated three different processes there: the definition of an object that can compute something, the starting of the computation, and the acquiring its result are three separate steps. For a more kind of concrete thing, your code might look like this. The inner kind of asynchronous function that you'd add to an extended task looks like this. So you have this is a future promise. It's similar to the future function call that I used earlier in the thing, but it returns an object called a promise, and Shiny knows how to handle them things. So we're going to start running with, say, when this input changes or when this reactive value changes. We're going to start that function running. And then later we might handle its result. Now I can show you how that looks in an app. So this is a slightly different app. I've only got a minute or so left to go. If I run this, I can choose from a few different ingredients. What it will do is it will take my choice of ingredient, call an API, and get the name of a recipe from that API. If I click on chicken, say, it returns the name of a particular stew from themealdb.com. If I click that, I can't actually click this details. I can click the details button, but it won't actually do any work until that API call's complete. And this is a sequential version of the code. It's only when the API call returns and the values have bubbled up through Shiny that any other work can be done by Shiny, right? That's just a bit of information. If I click that and then I click details, it's only when that finishes that that can run. If, however, I make the call to that API asynchronous and run and return a kind of future promise type thing, code looks like this. Future promise, call the recipes with this ingredient. When the user clicks the go button, use the current value of the ingredient as the argument to this inner function, right? So it's going to search recipes. It's done as a future, so it's asynchronous, running in a separate process. And when that result is available, we update this object, recipe details, which is like a kind of reactive value. So I've now got a asynchronous version of the same app. Oh, oh, I've lost my button. Oh, I'll tell you what I'll do. I'll open it in two sessions. Um, where are we? Did that open in a browser? Right. Okay. Right. I've got one in a web browser window and one in our studio's kind of mock browser. If I click that there and I click that there, it's only when this finishes that, sorry, no. Because this is the asynchronous version, I can start the processing in parallel. User one doesn't block user two, which it would have done in that earlier sequential version. Okay. So the processing starts at the same as soon as the button gets clicked. It's quite neat. So we're pushing work into background processes and then handling it when we come back when the results available. So that's extended task. There's good documentation about extended task, and the same concept is involved in Python Shiny for Python. So understanding how it works in the R version of Shiny will help you understand how it will work in the Python version as well. Thanks ever so much for coming along. Sorry about the delays and stuff at the start. That was all my fault from being Zoom inexperienced, I think. Yes, I said at the start that we have a conference and we have online training and things. There are discount codes here if you are interested in attending the conference or the training sessions. If anyone has any questions, and I can't see any questions in the Q&A, do let me know and I'll happily answer. I've got a little bit of time to answer. Okay, let's have a see. Oh, okay. I'm not getting any questions. Right. Oh, is it possible to get a copy of the slides? Um, I'd like to be able to refer back to these materials. I suspect that'll be possible. I will actually be presenting a much longer version of this as a workshop at a conference in next month. Um, um, yeah, I'll discuss that and come back to you. Um, Are there any questions about, oop, or indeed, has anyone had headaches in the past that they think asynchronous programming could solve for them? You know, has anyone built an app that only one person can use at a time? I've certainly experienced that before. No. Okay. Great. Thanks everyone for coming along. As I said, um, my name's Russ Hyde. I'm a data scientist working for Jumping Rivers. We do all manner of kind of consultancy in the data science and data engineering realm, from infrastructure to consultancy to programming training type work. And thanks ever so much. Right. Oh, someone's asked a question. Uh, is the issue of blocking handled automatically when you deploy to platforms like Shiny Apps? Um, I mean, you do need access to multiple processes in order to take advantage of um, asynchronous programming. I'm not entirely certain whether Shiny Apps provide you with more than one processor. I, to be honest, I'd be surprised if kind of the entry level tiers do, but the professional level tiers definitely do, as long as you configure them appropriately. Other things like Posit Connect, you can readily make multiple processors available. Um, thank you for your question. Okay. Right. Thanks ever so much. Make a comment on LinkedIn or Blue Sky or wherever it was that you found details of the talk, because I'd like to hear some feedback if possible, if you think it's beneficial or could be improved. Anyway, thanks a lot. I'm going to close the session now.